So I will provide you a link to video recordings. And I think, and what else? And I would like to send you, just a moment, an invite to Telegram chat. If you'd like to ask me questions outside our lectures or classes, then you are free to do so in Telegram. Okay, I think that's about. Okay, just I will present myself. My name is Boris Demyshev. I'm teaching stochastic calculus, econometrics, and time series in High School of Economics. You can find me in person in S517. What else? You can write me, you can ask me questions in Telegram, and I think what we will have some home assignments, and the final exam will contain two parts. The first part is by Kirill Alexandrovich Bukin about optimal control. I have nothing to do with this part, optimal control. And my part is, this is my part, is about stochastic calculus. And basically that's all. So your grades will be composed, you will have one grade for the whole course, mathematics for economists, and I'm responsible for some home assignments and stochastic calculus part of the exam. Basically that's all about the grading part of the course, and I think we can go straight to the subject. Or maybe one more formal point. My policy is to keep open all past exams. So just in 5 seconds, I will provide you a link to all past exams, so you can start to practice. And if you know everything, you are free to go to theater or cinema. So just a moment, I will provide you a link to all exams, all past exams I have sent. I will post the link twice. So if you can solve all past exams, so my lectures and classes probably are useless for you. But if you open past exams and see something new, then welcome. Okay, basically, I think that if you have any questions about the course, then please be brave and ask me your questions. But basically, my part, some home assignments, stochastic calculus, just a part of the exam. Basically, that's all what I will grade. And all materials, past materials are free. You can just open and solve. How many home assignments are we going to have? That a little bit depends on my abilities, because now I'm preparing a linear algebra course for Coursera. So it's a little bit hard. Normally, I think either, I think 2 or 3, maybe, I think 3, something like this. Will we have more lectures of optimal control? A question by Ruslan. As far as I know, that the answer is no, but it's not my part. My business is stochastic calculus. So probably you will have some office hours by Kirill Alexandrovich before exam, but it's better to ask him about optimal control. My part is stochastic calculus. So as far as I know, the answer is no. In one exception of just one office hours before exam, but it's better to ask him directly. Optimal control will be in the exam. Yeah, I think, yeah. Yeah, there are two parts, so you can look through past exams. Okay, maybe there are some changes. Okay, I will. Okay, maybe I'm wrong, but okay, yeah, maybe there are some. Okay, you know more than me in that case. So my only point that I do home assignments and exam on stochastic calculus. Okay, I will ask booking because this is something new for me, that this year optimal control is part of another guy. That's fine. Okay, let's start. So it's better to ask them. Okay, I have nothing to do with optimal control. All past experience that it was included as a part of the exam. Okay, I will ask and tell you next week. But my main idea that, honestly speaking, I have nothing to do with optimal control. But all past years, that was organized like this. Okay, so okay, I will ask booking about the structure, but maybe so let's wait 1 week or maybe less. Maybe I will meet him today and I will post the answer in the Telegram chat. Okay, so let's go on. Let's go straight to the topic. So basically, our course structure will be the following. First, I will introduce or maybe check your knowledge. I don't know yet your level of understanding, but I need sigma algebras. And I need a conditional expectation of some random variable with respect to sigma algebra. Next, we go on to martingales. Not today, but the structure of the course. Next, we go on to Wiener process. Next, we go to the stochastic integral, or ETAS integral, and some main properties of this stochastic integral, like ETAS lemma and other properties. Next, we go on to some stochastic differential equations. And we finish by a short introduction, just a very short introduction to some financial models. You will have a special course dedicated to derivatives, but my part is mathematics, not financial modeling. So a little bit in a small introduction to Black-Scholes model. Okay, so this is a big structure of our course. Sigma algebras, we will use them to calculate conditional expected value with respect to sigma algebras or other random variables. Then martingales, Wiener process, also known like as Brownian motion. Brownian motion. It is integral, it is lemma, so something like integral from 0 to t AU dWu. It is lemma, stochastic differential equations, and short introduction to Black-Scholes model. This is a main structure of the course. Let's go on. Okay. Just okay. Let's continue. Okay, first big topic is sigma algebra. Sigma algebra. First, I will. What book would you recommend us to get? Okay, I have a question. Yeah, what about books? I think there are the problem with the course is that the topic is rather hard from the mathematical point of view, and basically we need to create a stochastic calculus in 6 weeks. That's much better than 6 days, but anyway, it's a very small amount of time. So the problem is mathematically, it's very intensive subject, and I will not go deep into measure theoretical aspects of stochastic calculus, and that's why it's rather hard to find one book that is perfect for the course. But I think good choices are a book by it has a funny associations in Russian, Zastavnyak, a book by Zastavnyak. You can remember the author. Zastavnyak, basic stochastic processes. I think if I would choose one book, it will be the book by Zastavnyak. You may find also, I think it's Paolo Baldi. So I think that's the first recommendation. So if you prefer to read one book, then that's a choice. If you would like to have more mathematical details, so let's say one book. Could you recommend one book? Yes, I am. Yeah, the second one is Baldi. I don't remember, it's called as Introduction or Stochastic Calculus. So let me Google a little bit the exact title. Baldi Stochastic Calculus. I think it's, yeah, it's Stochastic, it's not Introduction. Baldi Stochastic Calculus. Stochastic Calculus. Calculus. If you like more math. If you like to go into finance application, yeah, Paolo Baldi. Paolo Baldi. Yeah. If you'd like to have most financial applications, then I would recommend either Shriv. That's Shriv. I think it's stochastic calculus. Yeah. Shriv, also called. Let's check me the exact title. Stochastic calculus for finance. Stochastic calculus for finance. It's a big. These are big books. One's first book and second book, and so this is for financial applications. And I think Michael Steele. I think it's Michael. Just a moment, Michael Steele. Stochastic calculus, also stochastic. Just a moment. I will write the exact name of the book. Yeah, Michael Steele. Stochastic calculus and financial applications. So I think if I have time to go through one book, so that it will be Zastavnyak Basic Stochastic Processes. If you are strong in mathematics, then you can choose Paolo Baldi. If you'd like to go on into quantitative finance, and that's your, so if you'd like to choose this field, so I would opt for Shriv Stochastic Calculus or Michael Steele Stochastic Calculus and Financial Applications. Oh, okay. Yeah. Now let's go back to sigma algebras. Sigma algebras. Oh, without S. Okay, idea. First idea, because formal definition is it just follows the idea. Intuition. We'd like to have a way to provide knowledge, to describe knowledge. So idea, sigma algebra. Sigma algebra is a way to describe information of a rational agent. So the idea is to describe information we'd like, to describe what we know, what we do not know, and if we go in technical details, so we just provide a list of all events. So sigma algebra is a list, a collection, a list of all events that let's have more intuition first, and then I will provide, obviously I will provide a formal mathematical definition, but let's start with intuition and not with formalism. Okay, sigma algebra is a list of all events, all questions. Let's even say the list of all questions, because every event basically just a question. Tomorrow it will rain. Will it rain tomorrow? We can state every event as a question. Okay, sigma algebra is a list of all events, all questions that a rational individual can answer for sure. Let's provide an example. And then after the example, I will provide a formal definition. Don't worry, because I know that a lot of you would like to have a formal definition. Wait a little bit. Let's develop intuition first. That's my idea. Okay, let's imagine that you throw a die. So you throw a fair die. So it's a fair die. You throw it once. So you have one throw. Imagine that you do not observe the outcome. Imagine that I just throw a die. I don't have a die here, but okay, I throw a die. And you ask me just two questions. You ask me first question. Let's denote by X. X is the result of the toss. Okay, X is the result. So the first question you ask me is X equal to 6, and I provide you the answer. You have my answer. I answer your question. Then you ask me whether X is greater than 3, and I answer your question. And let's describe your information now. So what is sigma algebra? Is a set, a collection of all questions that you can answer now. So sigma algebra. So that is your information. You know whether X is 6 or not. You know whether X is greater or equal than 3. Okay, and let's describe F. F is a sigma algebra, is a set of all questions you can answer, the set of all events you can distinguish for sure. So the set of all questions you can answer, or the set of all events that you can that you are able to tell whether they have happened or not. Let me provide some examples to make our lecture a little bit more interactive. I will provide you two examples of events. A, x is equal to 2. And the second one, x is less or equal than 2. I have two events, A and B. Can you for sure tell me, knowing you have all this information, so you have my answer, Imagine that you have my answer to the first question and the second question. And now I ask you whether x is exactly 2. Can you answer this question for sure or not? Or I answer you whether B has happened or not. Can you answer this question for sure or not? So my question is, do you know whether A has happened?
No, not for sure.
Yeah, there are two cases, or maybe, yeah, there are two cases. Yeah, right. I don't know who has answered, but the answer was correct. Yeah, not for sure, because, for example, if my answer was yes, so if my answers were yes for the first question and yes for the second, then you can conclude easily that x is not 2. Okay. Yeah. Okay. Anyone?
Yes, yes.
Yes, yes.
Yeah. But if my answers to you were no, then you are in doubts. You are not sure. Maybe it was 1, maybe it was 2. So you are not sure. Okay. So that's why A does not belong to the sigma algebra of your information. Yeah, let's consider other, because there are 3 cases. I also may answer you no, yes. Yeah, the answers yes, no are not possible. If x is 6, then x cannot be less than 3. So in this case, no, yes, you can answer that A has not happened, but A, so whether the event belongs to the set, the collection of questions you can answer for sure. That's important, this for sure. That's for sure, that is important in the definition. So sometimes you can answer, no is an answer. Yeah, you can answer, no is a good answer. But in this case, you are not sure. So this event A does not belong to the sigma algebra F. But in any case, you can answer about the event B, because if I answer yes, yes, has B happened in the first case?
No, what happened?
No. If I answer, if you have information from me, no, no, then you can conclude for sure that B.
Yes.
Happened. That be
Yes.
happened. Yeah.
Yes, has happened. No, yes. Then
Be not
has
happened.
B happened?
No, no.
No. And in any case, you have enough information to check whether B has happened. Anything may happen. You could have, so in any case, your information is sufficient to answer the question B, whether x is less or equal to 2. So in this case, B belongs to the sigma algebra. Okay, so that's very easy. Sigma algebras is a way to describe information you have. In sigma algebra, you just list all events that you are able to check for sure whether they have happened or not happened. Okay, the intuition is clear. Anyone?
Yes.
Yes.
Yeah. Okay, so let's go to formal mathematical definition. So math. F is a sigma algebra. F is a sigma algebra if. Let's imagine what can do a rational individual. Rational individual, obviously, for sure, he can say that nothing has not happened and something has happened. Yeah, that's so trivial that it's even hard to grasp. So trivial that it's even hard to understand. Something has happened. Yeah, something has happened. First is very something. Something has happened. So it means that the omega, the whole set of outcomes, belongs to our sigma algebra. Nothing has not happened. So empty set belongs to our sigma algebra. You can for sure answer that or to this question. And then you can do some logical operations. So if you know that A has happened, you know that B has happened. So you can conclude that A and B has happened, A or B has happened. So you can do logical operations. So basically, if A1, A2, A3, A4 belongs to F, so you know whether A1, A2, A3, A4, and so on has happened. You can calculate any combination of them. So for example, if you know that tomorrow it will rain, you know that tomorrow it will be less than 10 degrees of Celsius, then you can conclude that tomorrow will be rain and less than 10 degrees of Celsius. So if you know about event A1 and you know about event A2, you can combine them. You can make logical conclusions if you are a rational individual. So if you have you know about events A1, A2, A3, A4, and so on, then any event B that can be expressed, any event B that can be constructed, that can be constructed from A1, A2 using what logical operations you know intersection, you know union, you know complement. Yeah, you can take union, you can take intersection, you can take complement, countably many operations. Yeah, countably many. Let's be precise. Countably many operations. Belongs to B, belongs to F. So basically, there are only two requirements for sigma algebra. First, you know about trivial events. Something has happened, nothing has not happened. And if you know about some events, then you make logical conclusions. And if you look in many books, if you open the book by Baldi, the book by Zastavniak, and every book, you will see that this simple logic is, I don't know why. I don't understand why they first give the formal definition and then they try to explain why it's normal. So if you go to any book, you will see the following definition. F is called sigma algebra. Sigma algebra. If, let's say, empty set belongs to F, if A belongs to F, then complement belongs to F. And if A1, A2, A3, and so on belongs to F, then union of all these sets belongs to F. So if you look in any book, then you will encounter this definition. Basically, that one is easy to understand, because what does it mean I'm rational? I'm rational, that means I know some trivialities, that something has happened. Obviously, if you have thrown a die, then something has appeared. Yeah. So I know trivialities and I can make conclusions. So the second idea, I can make conclusions. And in book definition, because it's always, I don't know, maybe it's a Bourbaki tradition, but sometimes authors do prefer to state minimal requirements, necessary and sufficient conditions. And if you can take complements and unions, then you can describe intersections like complement of union of complements and so on. So indeed, this requirement that intersections and complements belongs to F is a little bit, it's okay, but you can state less, and book authors prefer to state less. That's equivalent to a intuitive definition. Okay, let's provide.
Oh, I have a question. Could you please say why is x equals 2 is not and does not belong to sigma algebra, if we can answer the question? I mean,
no, you can't answer the question for sure. Let's go back to this example. You have Mike, so I throw a die, you don't observe the result. So once again, the setup. I throw a die, I don't show you the result. So I have, where is my die? No, I don't see. Oh, maybe. Okay, yeah, there it is. Okay, I have thrown a die. You ask me the first question. Ask me the first question in our protocol. You have a protocol. You should ask me the first question.
Is the number that you get 6?
No. Ask me the second question.
Is it more than 3? More or equal?
No. And then I ask you a question. Is X 2?
Maybe.
Have enough? Maybe. So you cannot answer the question for sure. So you cannot determine for sure. You cannot be sure that X is 2 or X is not 2. So you can not determine whether this event, X is equal to 2, has happened or not happened. And by the intuitive definition of sigma algebra is a list of events about which you are completely sure in any situation, you are sure whether they have happened or not happened. This event A, X equals 2, your information may be not enough to check whether A has happened. Maybe it's enough. Yeah, if my answers would be different, then it will be the other case. But in the definition, for sure. Okay. Yeah, that's fine.
So any sigma algebra depends on the protocol.
Yeah, obviously. Sigma algebra is a way to describe information. So I have full information. I know the result of the toss. Yeah, here it is. I know the result of the toss. So my sigma algebra, my list of questions that I can answer is bigger than yours, because you can answer just a small subset of questions. And if I observe completely, yeah, see, I observe completely the result of the toss.
So
Yeah,
if
I see. And obviously, sigma algebra, my knowledge is in this particular experiment is bigger than yours. So my sigma algebra contains more events than your sigma algebra. Yeah, the main point, sigma algebra is a way to describe information of a rational agent. Masha knows whether it will rain tomorrow, and Pasha knows whether it will rain tomorrow, whether the dollar will be, I don't know, greater than 100 rubles tomorrow. And so Pasha knows more than Masha. And sigma algebra of Pasha, in this case, contains more events than the sigma algebra of Masha.
So we change x more than or equal to 4, the sigma algebra would change.
Okay, let's calculate one more example. I think that will answer your question. So, okay, let's calculate some more examples. So let's calculate the sigma algebra in the first example. Example continued. So let's calculate it explicitly. So x equal to 6. I can answer this question. You can answer this question because you know this information by protocol. Okay. What else? X is greater than 3. This event, you know about it by protocol. Okay. But you are a rational individual and you can do conclusions. Okay. So basically this, if we describe it in terms of simple events, in terms of outcomes, that is one outcome 6. This is just outcome 3, 4, 5, 6. Yeah, if I describe in outcomes, this is outcome 6. This is outcome 3, 4, 5, 6. Okay. If I'm rational, if I can do, you are rational, so that's your information. We start, then you can do conclusions. If you know about whether 6 has happened, you know about whether 3, 4, 5, or 6 has happened, then you can do conclusions. Yeah, you can say that x less than 6. Can you, if you know about whether x is 6, can you do conclusions about these events? Can you conclude that this event has happened or not happened?
Yes.
Yes, it hasn't
Yes,
happened.
because basically it's the complement of x equal to 6. So if you know about the event x equal to 6, then you know about the opposite event. Yeah. If you know that it will rain tomorrow, then you know whether it will not rain tomorrow. Yeah. If you are sure about that, if you know, just a moment. Okay, so I can conclude that 1, 2, 3, 4, and 5 is also in F. Let's go on. You can, if you are sure about, let's call this event A, this event B. So if you are sure about the event A and event B, then you can be, then you for sure know about the complement of event A complement, and you are sure about the event B complement. B complement is x is less than or equal to 2, or we have only 2 elementary outcomes, 2 primitive outcomes, 1 and 2. So we need to add 1 and 2 here. Okay, what else? You can, for example, if you know about A, about B, you can, for example, check whether A has happened, but B has not happened. Yeah, you can combine them like A intersection, no, B intersection A complement. Yeah, it's a combination of A and B. You can make logical conclusions. What is B intersection A complement?
3, 4, 5.
Yeah, it's 3, 4, 5. So we have 1, 2, 3, 4, 5 more. Who can provide more events, more conclusions, more logical operations? So what we can do?
Complement of this one, the last.
Yeah, we can take complement of this one, B intersection AC complement. Yeah, it will be 1, 2, 6. Okay, what else?
It definitely could be any combination of numbers.
Not any, not any. You are wrong. So, for example, you can never obtain. So let's solve it a little bit in a more systematic way. This is 1, this is 2, this is 3, this is 4, this is 5, this is 6. By no means, you have no information to distinguish 4 from 5. Never. If I ask you whether it was 4 or 4 or not 4, you will never distinguish 4 from 5 given your information, because if it's not 6, then it gives you no information about whether it was 4 or 5. The second event B also cannot be used to distinguish 4 from 5. So you can never for sure answer the questions whether it was 4, because 4 from your point of view, given your information, is indistinguishable from 5. Also, it's not distinguishable from 3. Yeah, because you have no means to distinguish 3 from 4. Yeah, no question could be used to distinguish.
Yeah.
And also some other points are indistinguishable. If you look at 1 and 2, you can never distinguish 1 and 2. You can distinguish 6 from 1 and 2 because 6 is separated in your knowledge. So you have, let's say, 3 chunks, 3 blocks that cannot be divided further. So you will have all possible combinations, but not of all elementary events. You are right in some sense that we will have all the combinations, but not all the combinations from all primitive events like 1, 2, 3, 4, and 6, but we will have all combinations of block. Yeah, you are right. Yeah, that's a good idea. Basically, yeah, I would point that, yeah, it's very good intuition that we can combine. So we can combine in any way, but what we can combine in any way, what we can distinguish, we can combine blocks. So all combinations of blocks. And so now it's easily to construct the whole list. The whole list will be 1 and 2, 3, 4, and 5, 6. Let's combine blocks by 2. 1, 2, 3, 4, 5. 1, 2, and 6. 3, 4, 5, and 6. So we have combined blocks by 1, by 2, all the 3, and no blocks. Okay, so this is a full sigma algebra in this case.
May I ask a question, please?
Yes, yes,
Oh.
yes. My main advantage over a book by Baldi or by Zastavnyak that I can answer questions and I can joke, but anyway, everything is in the books. So if you have questions, do not be shy. Be brave enough to ask them, because that's my main idea. So if you can, my first point, if you can go and solve all exams, you can solve all. I don't know. You go through the book by Zastavnyak and you say, "Oh, I know this book," so you are fine. So don't bother to spend your time during my lectures and classes. So be free. Life is good for many things, not only stochastic calculus. Yeah, please ask your question.
Okay, thank you. I will be brave then. So how did and those three first events, 1, 2, 3, 4, 5, and 6, how did we get them?
How
They're
do
like
I get
even
them?
or what?
So my sigma algebra is a minimal sigma algebra that contains answers to my questions. My initial questions were x greater than 3, 3, and x equal to 6. So I know this information by the protocol. Yeah, I have a protocol, what I know. So by construction, I should include these two events. And then, so let's draw them. If I have nothing, so let's start in a very primitive way. If I have no information, so let's imagine I have no information. I know the rules of the experiment. So I know that the die is thrown. Okay, I know that the die is thrown, but I do not observe any result. What information do I have? I'm a rational guy that for sure I cannot distinguish these primitive events, outcomes. 1, 2, 3, 4, 5, and 6 are indistinguishable for me. So for this case, when I have no information, my sigma algebra contains just two events. Nothing, empty set, and the full omega. Or if I write in full, empty set, and 1, 2, 3, 4, 5, 6. So that's the most simple sigma algebra. The minimal sigma algebra should contain two events. If I'm a rational guy, I can for sure tell that this has happened. X, if you have thrown a die, if you have thrown a die, then for sure something has appeared on the die. So this event has happened. And this event has not happened. So that's a very primitive sigma algebra. The most minimal, the primitive sigma algebra contains two events. And now let's go back to our protocol. In our protocol, I should add to this chunk of all 6 outcomes united, I add 2 pieces of information. Oops, I know whether x equal to 6. Yeah, it's 1, 2, 3, 4, 5, 6. And I know whether 3, 4. So this is my new information. And then if I try to break the set of my events into non-overlapping chunks, into non-overlapping blocks, I see that, let me change the color probably. So I see that I can cut 6, yeah, because I have this event x equal to 6, so it's here. So I can construct the opposite of this event. Then I try to cut. So basically, how I obtain these 3 blocks, I check what I know, and I try to see which outcomes I can distinguish and which outcomes I cannot distinguish. So I will try to break further. I construct antonyms, and I see that in any case, 1 is indistinguishable from 2. On any line, 1 and 2 are linked. On any line, 1, 3, 4, and 5 are linked. There are no questions. There are no questions that could be useful for me to distinguish 3 from 4 or from 5. And this is the last piece of information. So they are here. And then I blindly combine all the, combine everything. Okay, so first, this is omega. This is my question 1, x is 6. This is my second question by protocol, x is greater than 3. And then I combine all of them. I try to make the smallest chunks of information as possible. Basically, that's right. That's okay. Yeah.
Yes. So basically, depending on the answers on those two questions, 6
Yeah,
x equals to
yeah,
6, 6 more
yeah.
3 than 3, and x less or equal than 2, we can basically obtain those three sets, basically. Because if we say that x is not equal to 6, but it's more than 3 or equals, then it's either 3 or 4 or 5, right?
Yeah, yeah, yeah.
Okay,
You can
thank
do logical operations. Yeah.
Thank you.
Okay, let's if you for example, we can state our first theorem. Yeah, our first theorem. If sigma algebra F is finite, obviously there are infinite sigma algebras. If sigma algebras is finite, then it contains 2 to the power of n events. So in our case, it contains 1, 2, 3, 4, 5, 6, 7, 8.
Maybe you
events.
wanted to say no more than 2 to the power of n events.
Let's say 2 to the power of k. I have not specified what n is. I don't say that it's not the number of no. My idea was not that I just take 2 to the power of 6. It's 2 to some power, some power. K is not a is a number of blocks. Yeah. So k is a number, is the number of chunks of indistinguishable outcomes. In my case, I have 3 chunks. This is the first chunk. 1 is indistinguishable from 2. 3 is indistinguishable from 4 and 5, and 6 is separate. Yeah. So in this case, the total number of outcomes is 6. Yeah, and the number of events in the sigma algebra of events in the sigma algebra is not 2 to the power 6. Yeah, it's 2 to the power 3 because I have 3 blocks, 3 chunks. Okay, so this k is a number of blocks, not the number of outcomes. Okay. Why it's always 2 to the power k, where k is a number of chunks? Because if you write chunks first, then according to the formal mathematical definition of sigma algebra, you can combine, you can take unions of these chunks, and basically you can for each chunk you can either include it or not include. So you have events like plus plus plus. All 3 chunks are included. That is 1, 2, 3, 6 in our case. It's like plus, minus, plus. Yeah, it's like 1, 2, 6, and so on. You have two options for each of 3 points, and then you have 8 events in the sigma algebra. And the proof is more or less, if you understand the logic, that you can combine, you can do rational conclusions, then the proof is, you can see it. Yeah, you either take each chunk or either you don't take each chunk. Okay, let's go on. Okay, let's go on to random variables. Next definition. First intuition, and then formal definition. So my idea, my main goal is to provide intuition first, because the subject is rather complex and You can find definition in every book. So you just open the book by Zasternak, you see the definition, the format. I don't like to spend my time to, but I will give you honest definitions, but be sure to check the book. So first, intuitive definition. The random variable x is measurable with respect to sigma algebra f if f contains enough information to state the value of x, Let me provide some example. Trivial example, yeah. Let's continue our example. Continue it. Let's imagine that f is the sigma algebra generated by two questions. X is equal to 6. X is greater or equal than 3. Imagine a random variable y that is equal to 5 if x is equal to 6, is equal to 0 if x is less than 6. Then two questions. First question, is f sufficient to find the value of y? And the second question, is f sufficient to find the value of x? You know the information supplied by the protocol. Can you state the value of y? Do you know the value of y?
Yes.
Yes, obviously, because you know whether x equal to 6, then you know whether y is equal to 5, okay? Yeah, because you know about the event x equals 6, then you know the value of y. Just check your knowledge. If you know that x is 6, then the value of y is 5. Yes. But is your information sufficient to recover the value on the die?
No.
No. We mean for sure, yeah?
Yes.
To state the value of x for sure, yeah, for sure. Because sometimes you have enough information to state the value of x, but not always. So here the answer, no. Okay, so you have sufficient information to find the value of y, exact value, and you have no your information is not sufficient to find the value of x. So we say that y is measurable with respect to sigma algebra f, and x is not measurable with respect to sigma algebra f. Formal definition is just the generalization. What does it mean? I can find the value of x. From formal mathematical point of view, you know the value of x. That means that you can compare x to any number. What does it mean? I know, I know the temperature today. So that means I can compare this variable with any number. I can say you whether current temperature is less than 20 degrees. I can tell you whether the current temperature is less than 5 degrees. I can tell you whether the current temperature is less than 0, and so on. Basically, if I know the value of a random variable, that exactly means that I can compare it to any number. So the formal definition is the following. A random variable that is measurable with respect to sigma algebra F if for any real number t, the event that is less or equal than t belongs to the set of events I know. Okay, so that means basically this definition is consistent with our intuition, and it means I can compare random variable with any number if I'm able to compare a random variable with any number. So basically, I know the value. Okay, and once more, maybe notation. It's not a definition, it's notation. We say sigma of ABC. So if ABC are events, then this is the smallest sigma algebra that contains A, B, and C. And if X, Y, and Z are random variables, then sigma of X, Y, Z is the smallest sigma algebra such that X, Y, and Z are measurable. Measurable with respect to it. That's a notation. So let's solve. So we have, I think, seven minutes. Let's solve some more exercises to better understand what it is. Exercise. So imagine that yeah, imagine the following experiment. Imagine the following experiment. Imagine the following experiment. You start at 0 and you make one of the 4 possible steps. Either the particle goes up, either it goes right, either it goes down, either the particle goes left. So omega consists of 4 elementary outcomes. Either the particle will go up, down, left, or right. And just a small remark, but maybe it's important. Sigma algebras have nothing to do with probabilities. Honestly speaking, I need no probabilities. I need no measure to work with sigma algebras. Probabilities are necessary to describe to find expected values. But my point is that we can speak about sigma algebras and find and check whether we know something without assigning probabilities. So we don't need to specify whether these events have the same probability or whether the probability is different. So basically, it has for the moment nothing to do with probabilities. Probabilities are necessary to calculate expected value, but we have no expected value yet. Okay, and X and Y are coordinates of the particle after the step. And my question is calculate my first question, calculate sigma of x, calculate sigma of x plus y. So that is my question. So let's start. Okay, the goal is clear. I'm the guy, imagine, I'm the guy. What is my knowledge? I know, first question, I know x. I do not observe completely the position of the particle, but I know the x coordinate of the particle. This is my information. Yeah. And if I know the x position of a particle, then this is right, left, up, and down. Okay. And if I know the x position of a particle, then for sure I can distinguish. So let's once again use this technique to unite outcomes in indistinguishable blocks. Yeah. So if I have LURD, so if I know the value of x, for sure I can distinguish U from R. Yeah, if I know the x position of a particle, I can distinguish U for R. So U and R are not linked. But if I know the x position of a particle, so what should I draw here? Which positions are indistinguishable for me from my point of view? Which positions are undistinguishable? Yeah, U and D are undistinguishable. I should connect them. My information is not sufficient to separate U from D. Johnny Beck is completely right. I have enough information if I know X to separate L from R, to separate L from U and D, but I have no information to separate U from D. So my sigma algebra, I have 3 chunks. So my sigma algebra will once again will contain 8 events, L, U and D, R, and all the possible unions like LR, LUD, what else? LR, LUD, RUD, empty set, and LURD. Yeah, 8 events in total. If, for example, I know the value of x plus y, then which positions are indistinguishable for me? If I know x.
Vice versa, the LR, maybe.
You know the value of the sum. You don't know x, you don't know y, but you know only the sum, only the sum. So can you separate U from D? Can you separate U from R? What can be separated, what cannot be separated?
Suppose
if you
yes,
know the sum.
I suppose yes, because we can define whether it's negative or positive.
Yeah, you can see whether, so what are the possible values of a sum? Imagine this is 1, -1, -1, 1. It's one step. Let's introduce coordinate, yeah? So let's have the step has unique unit length. So in this case, either x plus y will be equal to 1 or to -1. There are no other possibilities. You cannot have it 2. The particle just does one step. So you cannot have the sum equal to 1. Yeah, you cannot separate U from R. You cannot separate L from D. And in this case, the sigma algebra is, first I will state chunks of linked outcomes, LD, UR, and all the combinations. I can make logical conclusions. So all the combinations, if I have 2 primitive events. What else should I write?
Their combination, which is the full set and the empty set.
The empty set and the full set. So I have 4 events in the second case and 8 events in the first case. Okay, I think basically that's all. So what we have studied today, we have defined what is sigma algebra. So we have described books, past exams. So if you prefer self-study, that's okay. Take a book, solve all past exams, and you are happy. What else? We have introduced sigma algebras. We have introduced what does it mean then variable x is measurable with respect to sigma algebra. And we have introduced notation sigma of event or sigma of random variable, the minimal sigma algebra that is sufficient to state whether A has happened, a minimal sigma algebra that is sufficient to state the value of a random variable x. So basically that's all. If you have any questions, then could you please explain why do we have L plus D? But basically, how could you separate L from D? The only 2 values of x plus y, if the length of the step is 1, the only 2 values are either +1 or -1. If I say you that x plus y is equal to 1, x plus y is equal to 1, then you can conclude that it's either U or R has happened, but you cannot distinguish between them. If I say that x plus U is equal to -1, then you can make a conclusion that L or D has happened, but you cannot distinguish them. That's why.
May I have a question, please?
Yeah.
I have a question about why x plus y can be equal to 2, for example.
In our case, we do only one step. My experiment, I take a particle and just one step. How it can be 2?
So you mean that we can go only up, only right, only down, and only left? And
yes, that's written here.
Clear. Okay.
So it's like,
what does it mean? Omega is equal to. That is what is omega in probability theory? It's a list of all possible outcomes. So if I say omega is U, D, L, or R, so I mean that there are only 4 possibilities. I haven't specified probabilities. I do not care about probabilities yet, but only 4 possibilities.
And so if we and so if we would have had 2 turns, what would be sigma algebra for example for 2 movements to the up?
If I once again, what is the experiment and what information do I have? So first, what is the experiment and what information do I have? So
the experiment just the same as this one, but we have extra step. We have 2 steps now.
2 steps. And what information do we have?
Again, we can move up, down, right, and left.
No. What you speak about omega or you speak about sigma algebra?
I suppose I'm speaking about omega now.
If you speak about omega, then if you if you have 2 steps, you do 2 steps, then in this case omega will be UU, UD, UR, UL, and so on.
Yes, that's what I wanted to understand. Thank you.
Could you please explain one more time the case with simply 1x? why don't we why can we differentiate between?
Between what?
Could you please move upwards a bit? Yeah,
Yeah.
a little bit more, please.
Yeah.
Yeah, thanks. That the case when we couldn't differentiate between U and D, so we like
Yeah.
put it in one chunk. Why so?
Because you know only x. So what is sigma x? You know the value of x. X is what? X is horizontal coordinate. If you know x, I say what can be after.
X is not a, okay, I got it. It's not a variable, it's a coordinate, right? X is horizontal coordinate, right? And Y
X is variable.
vertical.
Stop. X, the terminology. X is variable.
Yep.
X is a variable. X is a variable. Its meaning is horizontal coordinate of a particle after the first step. It's a random variable.
Mhm.
You say X is not variable. No, X is a variable, and the meaning of X is horizontal coordinate of the particle after the first step.
Mhm.
Okay?
Mhm.
The terminology of probability theory is very clear here. X is called a random variable. Why it's a random variable? Because the value of X depends. X of U is 0, X of D is 0, X of R is 1, X of L is -1. Okay? X is a variable.
Mhm.
The value of X depends on the outcome. So it's a random variable, a honest, beautiful, powerful random variable.
Yeah, okay, thank you. But I simply misunderstood the problem from the very beginning. Thank you. I got it now. Thank you.
Okay, two more questions. One question from Simeon. All possibilities are outcomes, and all information that we know, the least. So the question is, so all possibilities are outcomes. Maybe the least of all, so every possibility of an experiment is an outcome. So the list of all outcomes, the list of all possibilities is omega. It's about the first question. The second half of the question is a little bit less clearly stated. All info that we know events. No, event is just some subset of omega, and our information is described by the sigma algebra list of events. So omega list of outcomes, F sigma algebra list of events that we are capable to distinguish whether they have happened or not. One more question from Johnny Beck. Could you please explain the intuition of adding 1, 2, 6 into previous example of sigma algebra? Just a moment.
If I can clarify, I mean, I understood that we made the logical operation and got 1 to 5, but
so x less, in our previous example, we know x less than 2, so it contains 1, 2, or 6, 1 and 2. We know whether x is 6, so we know this. We know that, so we can make a conclusion whether x is less than 2 or x is 6. So this is 1, 2, or 6. So it's or logical operation. So because this is included in sigma algebra, that is included in sigma algebra, we are rational, we can do logical conclusion or, and this belongs to our sigma algebra F.
But as soon as we answer that it's 6 or not, we get down to 1 and 2 without 6. Or am I wrong?
What is your question? Once again, can we answer this question? So let's imagine, let's check whether for sure we have yes, yes possibility, no, yes, and no, no. X equal to x greater than 3, x is equal to 6, x is greater than 3, x is equal to 6, x is greater than 3. Okay, if both answers were yes, can you answer my question? X belongs to this set. Can you answer?
Yeah.
So
yeah.
you have information, yes, yes. Could you answer the question X belongs to 1, 2, or 6?
Yes.
Does it belong? Yes. Okay. If answers were no, yes, does X belong to 1, 2, or 6?
Yeah. Still belong.
Does it belong?
Oh wait. No.
No. If I answer no, no, does X belong to the set 1, 2, 6?
Yeah.
Yes. So in any case, you have no doubts.
Mm.
The answer itself is not important. An event belongs to sigma algebra if you have enough information to check whether it has happened or not happened. The exact answer, whether it has happened or not happened, is not important. The relevant is your knowledge. You know about this event. You know. The answer no means you know about this event. So for sure you are you know about this event. Let's call it C for simplicity. So for sure you know about the event C, whether it has happened or not. So C belongs to the sigma algebra F. Okay.
Thank you very much.
Okay, so bye-bye. See you next time. If you have any questions, just be brave and ask me. Be sure to look through future exams, stochastic calculus part. I will ask Kirill Sanch about what has changed with optimal control this year, but basically I'm not, this is not my sigma algebra, the optimal control part. So basically I may be wrong about this part. Okay, but I will, to be precise, I will check this and include this knowledge in my sigma algebra. So have a nice weekend. A nice evening. Yes, I will upload PDF notes to Telegram and maybe to the information system if I have enough time. And I will provide you a link to video recordings by Zoom. Okay, bye-bye.
May I have one small question
Yeah.
about sigma
Yeah.
algebra?
Algebra.
So suppose that we know that in our sigma algebra there is an event 1, 2, 6, and there is an event 1, 2. Can we obtain that separate event 6 is in our sigma algebra?
Yes. It depends on so you have 1, 2 in your sigma algebra. You have 1, 2, 6 in your sigma algebra, and because you have not described the experiment you have not described the experiment. Maybe you are working with a, let's say, 10-sided die, yeah. But in any way, even if you have not described the setup of the experiment, for sure, obviously, if this A,
it's just
B,
for our task with six.
Yeah, but my point is that even this is not important. This is not important. Even if I work with 10-sided die, so for sure I can make logical deduction. So, and I can say that B intersection A complement belongs to F, but B intersection A complement is just 6. So 6 belongs to F. In the definition of sigma algebra, you can combine events in any way. Complements, unions, intersections, you are free to do anything. In formal mathematical definition, you have only unions, because using unions and complements, you can construct intersections, symmetric difference, and any set operation can be constructed using unions and complements.
Mhm.
Okay?
Yes, thank you for the answer. Now it is clear.
Okay, best wishes for all of us. Be healthy and study sigma algebras. Bye-bye.